Welcome to the fourth program on electrostatics. Today we shall be discussing energy and potential with respect to electrostatic fields. In the last program, we had discussed how to determine electric field intensity and electric flux density due to two methods. Number one, by Coulomb's law, and second method was by the Gauss's law. The Gauss's law was applicable whenever the charge configuration was symmetrical, but when the charge configuration is complicated or unsymmetrical, then we have to resort back to the Coulomb's law. There is yet another way by which we can find electric field intensity or electric flux density, and that is by scalar potential V. It is much simpler because it is easier to handle scalars as compared to vectors. We start off with the energy in moving a point charge in an electric field. The object here is to calculate the work required to be done by an external agent in moving a test charge Q0 from A to B under the effect of electrostatic field E due to charge plus Q along any arbitrary path APB between points A and B. The force experienced by a charge Q0 at P is given by Q0 E. To prevent the acceleration of the charge in the direction of the electric field, the external agent is required to apply a force F such that F is equal to minus Q0 E. If dW is the infinitesimal small amount of work done by the external agent in giving infinitesimal small displacement dl to the test charge, then dW is equal to F dot dl as shown in equation 4.2a. Hence, the total work done or the potential energy required by the external agent in displacing test charge Q0 from A to B is given in equation 4.2b, which is WAB is equal to line integral of F dot dl from A to B, which is equal to minus Q0 line integral from A to B of E dot dl. Next we come to potential difference and potential. If we divide equation 4.2b by Q0, we get equation 4.2c. Now WAB by Q0 or the work done per unit charge can be defined by another parameter, which is potential difference between A and B, which is VAB. Since the line integral of electric field is independent of path, the work done per unit charge or the potential difference is also path independent. The negative sign indicates that the work is done against the field. Now it should be noted that in determining VAB, A is the initial point while B is the final point. If VAB is negative, it implies there is a fall in potential energy in moving Q0 from A to B, which implies that work is being done by the field. On the other hand, if VAB is negative, then it means there is loss in potential energy in moving Q0 from A to B, implying that work is being done by the field. On the other hand, if VAB is positive, it means there is gain in potential energy in moving the charge Q0 from A to B, and this implies that the external agent is doing the work. Here VAB is independent of the path taken. The unit of VAB is joules per coulomb or volts, and the principle of superposition applies to the concept of potential also. We have already seen in the previous program that the electric field E due to a point charge located at the origin is given by equation 4.3, that is E is equal to Q upon 4 pi epsilon naught R square into AR. Putting this value of electric field in equation 4.2d, we get VAB as shown, and it is equal to minus of integral of Q upon 4 pi epsilon naught R square AR dot dl, integration being carried out from RA to RB. Since we have taken a spherical system, then the dl would be in the form of spherical displacement which is dRAR plus r d theta a theta plus r sin theta d phi a phi. And after simplifying, we get VAB equal to q upon 4 pi epsilon naught into 1 by RB minus 1 by RA, or VAB is equal to VB minus VA, where VA and VB are the absolute potentials of B and A respectively. Potential due to a point charge. The potential difference VAB may thus be regarded as the potential at B with reference to A. In problem involving point charges, it is customary to choose infinity as reference. That is, we may assume that the potential at infinity is 0. Thus, if RA tends to infinity, then VA is equal to 0, and the potential at any point RB due to a point charge Q located at the origin would be given by equation 4.5, that is, V is equal to Q upon 4 pi epsilon naught into R. Thus, the potential at any point is the potential difference between the point and the chosen point at which the potential is 0. This can be seen from equation 4.6, that is, V is equal to minus of integral of E dot dl, the integral ranging from infinity to R. If the charge Q is not located at the origin, but it is at a point whose position vector is R prime, then the potential VR at R is given by equation 4.7. Potential field of a system of charges. So far, we have considered the potential due to a point charge. The same basic principles or ideas are applicable to various other charge configuration. We take them one by one. First, for n point charges q1, q2, q3 up to qn located at points with position vector r1, r2 up to rn, then the potential at the point whose position vector is r is given by equation 4.8, which can be reduced into a summation given by equation 4.9. For a line charge, equation 4.9 converts into 1 upon 4 pi epsilon naught line integral of rho L r prime dl prime upon mod of r minus r prime. For a surface charge, it reduces to 4.11, and for a volume charge, it becomes Vr is equal to 1 by 4 pi epsilon naught volume integral of rho v r prime dv prime upon mod of r minus r prime. Here again, it should be noted that the prime coordinates are for the source point, while the unprimed coordinates are for the field point. So now we have two ways in which the potential at any point can be determined. First, if the charge configuration or the charge distribution is known, then equation 4.9 to 4.12, that is for n point charges or line charge or surface charge or volume charge, can be used. If electric field is known, then we can resort to V is equal to minus integral of E dot dl. Relationship between electric field and potential. Since the potential difference between A and B is independent of the path taken, therefore VAB is equal to minus VBA. If we add these two, that is VAB plus VBA would give us minus integral of E dot dl from A to B minus integral from B to A of E dot dl, and it would result in integral of E dot dl for the closed path, and its value is 0. Therefore, E dot dl for the closed path is equal to 0. This is nothing but the integral form of Maxwell's second equation for electrostatics. It shows that the line integral of E along a closed path must be 0. Physically, it implies that no net work is being done in moving a charge along a closed path in an electrostatic field. If we apply the Stokes theorem to equation 4.13, that is, if we want to convert the line integral to a surface integral, we get expression given by equation 4.14, and from that we can find that curl of E is equal to 0. This is the differential form of Maxwell's second equation for electrostatic fields. Any vector which satisfies equation 4.14 is said to be conservative or irrotational. Thus, an electrostatic field is an example of a conservative field. Now, from equation 4.2d, V is equal to minus integral of E dot dl. We can express E in the Cartesian coordinate system and similarly dl also in the Cartesian coordinate system. But before that, we differentiate the above equation and we get dv is equal to minus E dot dl, and when we expand E and L, we get dv is equal to minus Ex dx minus Ey dy minus Ez dz. Now, we also know that the change in V is equal to del V by del x into dx plus del V by del y dy plus del V by del z dz. If we compare equation 4.16 and equation 4.17, we get Ex is equal to minus del V by del x, Ey is equal to del V by del y, and Ez is equal to del V by del z. Or we can say E is equal to minus gradient of V. The significance of minus can be seen in figure 4.3, where the direction of E is opposite to the direction of the gradient of V. Electric dipole. An electric dipole is formed when two point charges of equal magnitude but opposite in sign are separated by a small distance, which is small compared to the distance to the point P at which we want to find the electric and potential fields. The electric dipole is a vector directed from negative to positive charge. If the charges are q and minus q separated by a distance L, then dipole moment P is given by equation 4.20, which is P is equal to QL as shown in figure 4.44. We will derive the expression for electric field due to an electric dipole. In the figure 4.5, we see there are two point charges q and minus q separated by a distance L and forming a dipole. We are required to find out the electric field at a point P. The field at point P due to both the point charges or the dipole consists of two components, one in AR direction and the other in A theta direction. There is no component in the A phi direction. The field at P due to the 2 point charges is given by equation 4.21, that is E is equal to q upon 4 pi epsilon naught r1 square into AR minus q upon 4 pi epsilon naught r2 square into AR2. The component of E in the AR direction is given by equation 4.22. Now, in 4.22 we have to determine the expression for cos alpha 1 and cos alpha 2. For that, we resort back to figure 4.5, where using triangle OAP, OA square is equal to L by 2 square is equal to R1 square plus R square minus 2R R1 cos alpha 1, which is given in equation 4.23a. Using this expression, we can find the expression for cos alpha 1. Similarly, using triangle OBP, we can find the expression for cos alpha 2. Putting the values of cos alpha 1 and cos alpha 2 in equation 4.22, we get the expression for ER, which on simplifying results in equation 4.23d. Now, since P is very far off from the dipole, for all practical purpose, we can say R is equal to R2 is equal to R1, and since R is much greater than L, ER can be put as q upon 8 pi epsilon naught R cube into R2 minus R1 into R to the power of 4 plus R square into 3R square, which reduces to q upon 2 pi epsilon naught R cube into R2 minus R1. Now, from figure 4.5, again we see that R1 is equal to R minus L by 2 cos theta and R2 is equal to R plus L by 2 cos theta. Therefore, R2 minus R1 is equal to L cos theta. When we put this value in the above equation, we get ER is equal to Q upon 2 pi epsilon naught R cube L cos theta. The A theta component of E is given by E theta is equal to E dot A theta, which on simplifying becomes Q upon 2 pi epsilon naught R square sin alpha 1. We need to find an expression for sin alpha 1 using alpha 1 is equal to alpha 2 and R1 is equal to R2 is equal to R. We get the expression of sin alpha 1 as L by 2 sin theta upon R, and therefore the expression for E theta reduces to QL sin theta upon 4 pi E naught R cube. Putting 4.23 F and E into the expression E is equal to ER AR plus E theta A theta, we finally get the value of E, which is P upon 4 pi epsilon naught R cube into 2 cos theta AR plus sin theta A theta, where P is the dipole moment equal to Q into L. So, we have found the expression for electric field at a point due to a dipole using the Coulomb's law. As we can see, it is a very tedious process. Now, we shall derive the same expression using the concept of potential. The potential at P is given by V is equal to Q upon 4 pi epsilon naught into 1 by R1 minus 1 by R2, which is equal to Q upon 4 pi epsilon naught into R2 minus R1 upon R1 R2. But since L is much less than R, therefore R2 minus R1 is approximately equal to L cos theta and R1 R2 is approximated as R square. Therefore, V becomes equal to Q upon 4 pi epsilon naught into L cos theta upon R square, which can further be simplified as V is approximately equal to P dot AR upon 4 pi epsilon naught R square. The dipole moment P is directed from minus Q to Q. If the dipole center is not at the origin but at R prime, we get V at R is equal to P dot R minus R prime upon 4 pi epsilon naught into mod of R minus R prime cube. Coming back to equation 4.26 and knowing that E is equal to minus gradient of V, and that is equal to minus of del V by del R into AR plus 1 by R del V by del theta A theta plus 1 by R sin theta del V by del phi A phi. So, we are required to find out del V by del R, which will be obtained by differentiating equation 4.26 with respect to R, keeping theta and phi constant. For finding del V by del theta, we differentiate expression 4.26 with respect to theta, keeping R and phi constant, and the same is true for getting del V by del phi. Getting all these values and putting them in the equation and simplifying, we get equation 4.29, which is same as that obtained using the Coulomb's law. But now we can see that there is sufficient drop in the amount of labor required for finding out the expression for electric field due to a dipole. Energy density in an electric field. Bringing a positive charge from infinity into the field of another positive charge requires work, and this work is done by an external agent in moving the charge. Let us imagine that the external source carries the charge up to a point near the fixed charge and holds it there. Now, according to the law of conservation of energy, energy must be conserved, and the energy expended in bringing this charge into the position now represents the potential energy. For if the external source released its hold on the charge would accelerate away from the fixed charge, acquire kinetic energy of its own and the capability of doing work. In order to find the potential energy present in a system of charges, we must find the amount of work done by an external source in positioning the charges. We may start by visualizing an empty universe, and we wish to position 3 point charges Q1, Q2 and Q3 at positions P1, P2 and P3 as shown in figure 4.7. Bringing a point charge Q1 from infinity to any position P1 does not require any work because of absence of any field, that is W1 is equal to 0. The positioning of Q2 at a point P2 in the presence of Q1 requires an amount of work given by the product of Q2 and the potential at P2 due to Q1. If we represent this potential as V21, where the first subscript indicates the location and the second subscript the source, that is V21 is the potential at the location of Q2 due to Q1. Thus, the work required to position Q2 is Q2 into V21, that is W2 is equal to Q2 into V21. Similarly, the work required to position Q3 at P3 in the presence of Q1 and Q2 is given by Q3 into V32 plus V31, where V31 is the potential at P3 due to Q1 and V32 is the potential at P3 due to Q1. Thus, the total work done in positioning the three charges Q1, Q2 and Q3 at P1, P2 and P3 is given by WE is equal to W1 plus W2 plus W3 is equal to 0 plus Q2 into V21 plus Q3 into V32 plus V31. If we reverse the positioning of the charges, then we get WE is equal to W3 plus W2 plus W1 is equal to 0 plus Q2 into V23 plus Q1 into V12 plus V13, which gives us equation 4.31. If we add equation 4.30 and 4.31, we get the expression for WE, which is half into Q1 V1 plus Q2 V2 plus Q3 V3, where V1, V2 and V3 are the total potentials at P1, P2 and P3. That is, V1 is equal to V12 plus V13, V2 is equal to V21 plus V23 and V3 is equal to V32 plus V31. In general, if there are n point charges, then equation 4.32 can be converted into a summation given by equation 4.33a. If instead of point charges, we have the other charge configurations like line charge, surface charge and volume charge, then the summation in equation 4.33 becomes an integral, and for the line charge it takes the form of 4.34b, for the surface charge it takes the form of 4.34c, and for the volume charge it takes the form of 4.34d. The last equation, that is 4.34d, is the most general form for any charge configuration. Now, we know that the Maxwell's first equation is del dot D is equal to rho v, and putting this value in 4.34d, we get equation 4.35, that is WE is equal to half volume integral of rho v v dv, which is equal to half volume integral of del dot D v dv. Now, the following identity holds for any vector A and scalar v, which is given by equation 4.36. Putting equation 4.36 into equation 4.35, we get WE is equal to half volume integral of del dot Vd minus half d dot gradient of V dV. Applying divergence theorem to the first term on right hand side of equation 4.37a, we get the surface integral given in equation 4.37b, that is WE is equal to closed surface integral of Vd dot ds minus half volume integral of d dot gradient of V dV. Now, we know that for a point charge, V varies as 1 by r while d varies as 1 by r square. For a dipole, V varies as 1 by r square while d varies as 1 by r cube, and similarly when we have n poles, V varies as 1 by r to the power of n while d varies as 1 by r n plus 1. Hence, Vd in the first term on right hand side of equation 4.37a must vary at least as 1 by r into 1 by r square, that is 1 by r cube, while ds varies as r square. Hence, the first term on the right hand side of equation 4.37b must tend to 0 as the surface becomes large, and therefore equation 4.37 reduces to We is equal to minus half volume integral of d dot gradient of V dV. Now, since gradient of V is equal to minus E, putting this value in the above equation, we get We is equal to half volume integral of d dot E dV, and we can have other configurations like half of volume integral of epsilon naught into E dot E dV. And finally, we have equation 4.38 where we have the expression of We in various formats as half in volume integral of d dot E equal to half of integral of E naught mod of E square dV. From equation 4.38, we can define electrostatic energy density We, which is in joules per meter cube, as We is equal to d We by dV, which is equal to half d dot E equal to half epsilon naught E square equal to d square upon 2 epsilon naught J per meter cube or joules per meter cube. From the above equation, we can also write the total energy is equal to integral of We dV. In this lecture, we have discussed energy and potential with respect to electrostatic fields, where we have discussed energy required to move a point charge in an electric field, the concept of potential difference and potential, the potential due to a point charge and other charge configurations, the relationship between electric field and potential, the electric dipole, and the energy density in an electrostatic field. Hope you enjoyed the lecture. Thank you.